All right, welcome back to the deep dive. Today we're taking a look at something that's becoming more and more important in ML, and that's making sure our models aren't accidentally spilling secrets about the data we use to train them.
You got it. It's about keeping things private, which is kind of a big deal as these models get really good at what they do, especially when they're used with super sensitive information.
Yeah, totally. So we're diving into this new paper that focuses on a pretty cool idea called membership inference attacks. MIAs for short.
Ah, MIAs.
Right. It's basically like you have this trained model and you want to know if a specific piece of data was part of the group used to train it.
That's kind of like playing detective with your model. Like, hey, have you seen this data before?
Exactly. And what I found really interesting about this paper is how it shows that MIAs aren't just about protecting privacy anymore. They can also be used to double check if the training data was actually what it was supposed to be, like a little integrity check.
Yeah, that's a really cool way to think about it. Like, at first, everyone was worried about keeping secret stuff from leaking out, but now it's like, hey, we can also use this to make sure we're training our models on the right stuff.
Yeah, like imagine if you could audit a model to be absolutely sure it learned from the data you intended and nothing else.
That's huge, especially with all these new regulations popping up, like the EU AI Act. They really want to make sure everything's transparent and accountable when it comes to AI.
And speaking of accountability, the paper does a great job pointing out some of the, well, hiccups with the current methods. Like some MIA techniques need a ton of computing power and tons of data, sometimes even more than what was used to train the original model, which, let's be real, isn't very practical in a lot of cases.
You're telling me.
Plus, the way we usually measure how well these attacks work, using stuff like true positive rate at a low false positive rate, can be kind of hard to understand and compare, you know?
Yeah, there's definitely a bit of a balancing act there. You want to be really sure when you spot a privacy leak, hence the focus on low false positives. But it can be tough to really grasp what a tiny percentage actually means when you're dealing with huge data sets. Like a low true positive rate could still mean thousands of leaked data points.
Right. It's easy to get lost in the percentages and miss the big picture. So what does this paper do about it? Well, it brings two new things to the table. First, there's FSMEIA, a new type of MIA that uses few-shot learning to make things a lot more efficient.
That's a mouthful.
And second, they have this new way of measuring privacy leakage called log MIA, which is supposed to be way easier to understand. So that's what we're going to dig into today, figuring out how these new ideas can help us evaluate privacy in a way that's both practical and insightful.
Sounds good. So where do we start? Maybe with how they set up the whole problem, like they do in the paper with a formal definition of an MIA.
Yeah, good point. They lay it out in their equation 1, showing it's basically a yes or no question. You have a model, you have some data, and the MIA is just trying to figure out if that data was part of the model's training set or not.
Nice and straightforward. I like it.
Yeah. And before getting into their new stuff, they give a really cool overview of how research in this area has evolved over time, going back to the early days of shadow models.
The shadow model approach. Classic.
Right. The idea is to train a bunch of these extra models to kind of copy the target model's behavior. And then you can use these shadow models to guess if some data was part of the original training or not.
Pretty clever, but definitely resource intensive.
For sure. And then they move on to talk about loss-based techniques, which work on the idea that a model will usually have a lower loss on data it's already seen during training compared to, new data it hasn't encountered before.
Makes sense. The model's kind of like, oh, I recognize this, and it performs better.
Exactly. So they walk us through all these key papers showing how researchers have tried all sorts of things, like using the differences in loss values, Bayesian inference, looking at the model's loss landscape, setting thresholds based on how confident the model is in its predictions, using statistical tests, and even quantile regression.
Wow. So they've really explored a lot of different angles over the years.
Yeah, it's pretty impressive to see how much work has gone into this area. But of course, as they point out, there are still some big challenges. Like some of these cutting-edge MIAs can be really demanding, computationally speaking. They might need you to train hundreds of those shadow models, which is a lot of work, especially for those giant models everyone's using these days.
Yeah, and not to mention that some methods rely on having access to the entire training data set of the target model, which is often a big no-no in the real world.
Exactly. Privacy and data security are huge concerns, so that's not always realistic. And then there's the whole thing about evaluating these attacks, which we touched on earlier. Just looking at the overall accuracy of the MIA isn't that helpful in this case, is it?
Definitely not. You could have a really accurate model that's great at spotting data that wasn't used in training, true negatives,
Yeah.
but that doesn't necessarily tell you much about the actual privacy risk.
Right. It's the true positives that we really care about, knowing how well the attack can identify data that was actually used in training. And of course, we want to keep those false positives as low as possible, because those are the real privacy breaches.
Absolutely. Each false positive could represent a piece of sensitive information that's been inadvertently leaked.
And that's where this whole true positive rate at a low false positive rate metric comes in. But as the paper explains really well, it has its limitations.
Oh yeah, definitely. Like, what counts as a low false positive rate really depends on how big your data set is. And that makes it tricky to compare results across different studies. Plus, even a small percentage can translate to a big number of actual data points being exposed, especially with datasets as large as Wikitext, which they highlight in the paper.
And they even show this in their table 1, right, where they give examples of what these percentages actually mean in terms of raw numbers. It's a good reminder that even a seemingly low TPR can have serious real-world implications. So this is where they introduce few-shot learning, or FSL, as a way to address some of these issues.
Yeah, FSL is pretty awesome. It's all about teaching models to recognize new things with just a handful of examples.
Right, like imagine you're teaching a kid what a zebra looks like. You don't need to show them hundreds of pictures, just a few good ones, and they get the idea.
Exactly. It's all about leveraging what the model already knows to learn new stuff quickly.
And the paper does a good job explaining the standard lingo used in FSL, like N-way K-shot classification, where N is how many different categories you have, and K is how many examples you have for each category.
And they also talk about the support set, which is the small set of labeled examples used to train the model on the new task, and the query set, which is the unlabeled data you want to classify.
Yeah, and the goal is to come up with a function that can accurately classify those query examples, even with just a few examples in the support set.
It's like a crash course for the model.
Right. And they also briefly talk about the different ways FSL is done, like augmenting the training data, adapting existing models, or developing new algorithms that work well with small data sets.
So how does all this connect back to MIAs?
That's where their FSMEIA framework comes in. They're basically applying FSL to the problem of membership inference.
That's pretty neat. So instead of trying to figure out if a data point belongs to a certain category, we're trying to figure out if it was part of the training data or not.
Exactly. So you'd have a support set with a few examples that you know were either part of the training data, members, or not, non-members. And then you use this to try and classify the data in your query set. They specifically look at cases with 1, 5, or 10 examples in the support set, which is pretty limited.
So it's a true few-shot scenario.
Right. And they actually came up with 3 different ways to implement FMEIA. The first one is called FSMEIA transductive tuning, or TT for short. This one takes a model that's already been trained on a related task, what they call the victim model, and then fine-tunes it using that small support set with the labeled member and non-member examples. They also use a special term to make the model more confident in its predictions on the unlabeled query data. But one thing to note is that this method needs you to be able to actually change the victim model's parameters, so it's what we call a white box attack.
So you need to have access to the model's inner workings.
Exactly. Now, the other 2 implementations are a bit different. They're what we call black box attacks, meaning you don't need to mess with the victim model's parameters. These are called FMI simple shot, SS, and FSMI Laplacian shot, LS.
Okay, so how do those work?
So FSMEIA simple shot uses the pre-trained victim model to create these centroids, or average feature vectors, for the member and non-member classes based on the few examples in the support set. Then, for each new data point, it basically looks at its features and figures out which centroid it's closer to. The one that's closest gets classified as either a member or a non-member. Pretty simple, right?
Yeah, that makes sense. And what about Laplacian shot?
Laplacian shot builds on simple shot by adding a little something extra to the mix. They introduce a regularization term that encourages the model to not only assign data points to their nearest centroid, but also to make sure that data points that are close to each other in terms of their features are also classified similarly.
So it's like adding a bit of smoothing to the decision process. Makes sense.
Yeah. So that covers the FMEIA part. Now let's move on to the second big thing they introduce, the log MIA measure. Remember how we were talking about the limitations of using the true positive rate at a low false positive rate?
Yeah. It can be hard to interpret and compare across different studies.
Right. Well, they propose this new measure called log MIA, which they say is much more meaningful and easier to understand.
Okay, I'm curious, how does it work?
Their main point is that what we consider a low false positive rate really depends on the context, especially the size of the data set. So they suggest using a logarithmic scale that's related to the size of the data set to determine what a reasonably small number of false positives would be.
So instead of just picking an arbitrary threshold, they're making it relative to the data itself. Clever.
Exactly. And for the true positive rate, they use something called the TP log ratio. They explain in the paper that this metric grows faster than the traditional TPR, especially when the TPR values are small.
Why is that important?
Well, their argument is that even if you can only correctly identify the membership of a single data point, that's still a privacy concern. It shouldn't just be brushed aside as insignificant. The log ratio helps to highlight the importance of even those small successes in membership inference.
So it's like zooming in on those subtle leaks that might otherwise be missed.
Yeah. They also introduce a threshold called alpha, which basically tells you if there's any meaningful leakage happening based on this log ratio.
Okay, so they've got a new way to measure the number of false positives and a new way to measure the true positive rate. What's next?
Well, the cool thing is they actually define two different scenarios, or regimes, for evaluating MIAs using this new log MIA measure. Regime A is all about looking at the TP log ratio when you have absolutely zero false positives.
So it's the best case scenario in terms of accuracy. You only want to count those cases where the MIA is 100% sure.
Exactly. And if the TP log ratio in this regime is higher than their alpha threshold, they consider that a sign of a serious privacy leak.
Makes sense. And what about regime B?
Regime B looks at the TP log ratio when you allow a small number of false positives based on their new logarithmic definition. They actually define different levels of severity for the leakage based on how the TP log ratio compares to their alpha and beta thresholds.
So it's a bit more relaxed than regime A, acknowledging that some mistakes are inevitable in practice.
Right. And to show how useful this new log MIA measure is, they actually went back and reevaluated several existing state-of-the-art MIAs using it.
So they put their money where their mouth is.
Exactly. And what they found, as shown in tables 2 and 3, is that some of the attacks that were previously considered really strong didn't actually meet their criteria for severe leakage under regime A.
Interesting. So even some of the top performing methods might not be as foolproof as we thought.
Right. And then under regime B, they found that many methods actually did show significant leakage when viewed through the lens of log MIA.
Which again highlights the limitations of relying solely on the traditional TPR at a low FPR metric. It might not be telling the whole story.
Okay, so now let's talk about how they actually tested their own FSMEIA model.
Yeah, let's get into the nitty-gritty of the experiments.
So they use a few different data sets, including those image classification data sets CFAR10 and CFAR100, as well as a language modeling data set called Wikitext 103. For the victim models, they chose well-known architectures like WideResNet for the image data sets and GPT-2 for the text data.
Good choices.
Yeah.
Those are pretty representative of what's being used in research these days.
Yeah, and they ran a lot of experiments, like 500 trials for each setting, to make sure their results were reliable. They analyzed the log MA scores under both regime A and regime B, looking at all three of their FSMEIA implementations, TT, SS, and LS, and trying different numbers of labeled examples in the support set, 1, 5, and 10.
Very thorough. And did they mention anything about how they tuned the hyperparameters for their methods?
Yeah, they said they used a validation set, which is standard practice in ML. Basically, you use a separate portion of the data to fine-tune the model's settings before testing it on the actual test set.
Makes sense. So what were the results? Did FA live up to the hype?
Well, under regime A, as shown in Table 4, none of the FSMEIA models reached that severe leakage level. Their log MIA scores were all below their alpha threshold of 0.25. However, they did notice that the scores got slightly better when they used more labeled examples in the support set.
So having more data to work with does help, even a little bit.
Yeah, but accurately identifying members with 100% certainty is still pretty tough when you only have a few examples to go on.
Makes sense. It's like trying to solve a puzzle with only a few pieces. But what about regime B? Did they see any significant leakage there?
That's where things get interesting. In Table 5, they show that FSMEIA Laplacian shot achieved what they call moderate leakage. This means it could identify some members correctly, but not a ton more than the allowed false positives. But both FSMEIA simple shot and transductive tuning showed significant leakage across the different data sets. And in many cases, they could do this with just one labeled example.
Wow, that's pretty impressive. It seems like these few-shot-based MIAs can be surprisingly effective even with very limited information.
Yeah, and that's a key takeaway from their experiments. They basically conclude that their FSMEIA models, especially simple shot and transductive tuning, are way more efficient at finding privacy leaks compared to many existing methods. They can achieve significant leakage without needing massive computing power or huge auxiliary data sets.
Which is great news for researchers and practitioners who are concerned about privacy but might not have access to those resources.
Exactly. They also found that FSMEIA transductive tuning generally performed the best out of the three, likely because it can fine-tune the entire victim model based on the support data.
But that requires white box access, right?
Right, so it might not always be feasible in real-world scenarios.
True. So to sum it up, this paper basically gives us two awesome tools: a more practical way to carry out MIAs with FSMEA, and a more insightful way to evaluate those attacks with log MIA. It's a big step forward in making privacy evaluation more doable and understandable for everyone.
Totally agree. Being able to spot these privacy vulnerabilities is super important, especially as we use ML models in more and more sensitive areas. And having tools like SMEIA and LogMEA can help us better understand and address these risks.
For sure. All right, let's move on to our novel notions segment, where we brainstorm some cool extensions and future directions for this research. I think this paper, with its focus on efficient attacks and understandable metrics, opens up some really exciting avenues for exploration in ML security and privacy.
I'm all ears.
Well, one thought I had was, what if we used these efficient FSMEIA techniques to develop even better privacy-preserving training methods?
That's a really cool idea. Like, imagine using FSMEIA as a sort of lightweight check during training to spot any potential memorization of individual data points.
Exactly. If the probe starts to get really good at inferring membership for a particular data point or a small group of data points, that could be a sign that the model is starting to overfit to those examples. Then we could adjust the training process on the fly, maybe by adding noise or using differential privacy techniques more aggressively.
I love it. It's like a dynamic privacy shield that adapts to the specific data being used.
And the log MIA metric could be super useful here too, right? Instead of just getting a yes or no answer about whether there's a leak, you get a more detailed measure of how bad it is.
Right. That could help us fine-tune the balance between privacy and performance during training. Maybe we could even set a target log MIA score that the model shouldn't go over.
Awesome. Another thing I was thinking about is, how well would these techniques work with different kinds of ML models and data? This paper mainly focused on images and text. It would be cool to see how FSMEIA and LogMEA perform on things like tabular data or graphs with different model architectures.
Definitely. There's a whole world of ML out there to explore.
And on that note, given how efficient FSMEIA is, it makes you wonder if we could use these lightweight attacks in resource-constrained environments or even in real time against deployed models. That could be a game changer for constantly monitoring AI systems for potential privacy issues that might pop up after they're already out there in the wild.
That would be amazing. Proactive privacy protection at its finest. Well, it seems like this paper has given us a ton to think about. More efficient attack methods, more interpretable evaluation metrics, and a whole bunch of potential avenues for future research.
Totally agree. This is definitely a paper worth checking out for anyone interested in the intersection of ML and privacy.
Couldn't have said it better myself. You can find the link to the paper in the description below. Thanks for joining us on The Deep Dive.